I really like this problem because it helped me to see how all these pieces connect. You got four different techniques here, all approximating the same thing and getting very close answers to each other. So it's just a nice little understanding problem for myself there when I first worked this thing out. Now, here is all of my work for this problem in case you just need to see that at the beginning here. But for part A, it says write the equation with a tangent line. So we know we need a point and the slope. And so it tells you x equals 1. So there's my point, 1 comma 15. And then the slope at x equals 1 is the derivative, which is equal to 8. So once you have your point and the slope, find the equation of the tangent line, do your point slope form. And then it says use that to approximate f of 1.4. So just plug that in place for the x. Practice that without the calculator. You got your approximate y value right there. Because remember, around that point of tangency, that curve and the tangent line, they're very close to each other. So it's going to be a good approximation. Now, letter B, I kind of want to do this one from scratch with you, just on a blank sheet of paper. But typically, I'll jot this down here, and I'll kind of just go straight to that. And let me just share with you where those numbers are coming from right there. But this is our first time seeing a midpoint Riemann sum. Now, notice it says two subintervals of equal length, midpoint Riemann sum. Riemann sum, we know that means we're supposed to draw in some rectangles here. And you're going from 1 to 1.4. That's what your integral goes to. Now, it tells us two equal subintervals. So that means the bottoms of these rectangles are going to be the two rectangles of equal width. So like the bottom of this is going to be 0.2. The bottom of this is going to be 0.2. So right away, I'm going to go 0.2 times something plus 0.2 times something. That's the base of each one of those rectangles. And all the right, left, or midpoint Riemann sum stuff tells us is to simply know where to go to draw the height. Like if it says a right Riemann sum, you start at the right side of your interval and you go up to there and you use like the height of 14.5. If it says a left Riemann sum, you start the left side of your interval, you go up to the curve and use the first height is equal to 8. So when it says a midpoint Riemann sum, that just tells you to use the middle of those subintervals to get your actual height. So I guess if I kind of get rid of these 0.2s, so what you do, you just go in the middle between 1 and 1.2, that's going to be 1.1. And so like we have this curve right here. I mean, this thing just kind of keeps on going up and it's got an increasing curve. And so you just go in the middle between 1 and 1.2, you go to that 1.1, that's the midpoint of that. And that's where you go up to the curve. And that's where you draw the height of that rectangle over, which means the height of that rectangle is f prime of 1.1. That's the y value at 1.1, which is going to be 10. So when I do the area of that rectangle, I go base times height, that's 0.2 times the 10. And then the second subinterval in between 1.2 and 1.4, since it says a midpoint, you go smack dab in the middle of that. You choose the 1.3, and that's technically where you're supposed to go up to the curve. And once you hit the curve, that's the top of it. And so that's the height of that rectangle right there. And if you want to know how high up you went, that's the y value right there, which is that 13. So I couldn't really show you the midpoint thing, and that's where we're going to put the 13 right there. And I couldn't show you that on the other ones because we weren't given the middles of those intervals, of those subintervals there. So notice that these numbers here are the same as these numbers here. You don't need the picture for that. Typically when I do those, I'll start off, I'll go, hey, I'm going between 1 and 1.4. And then it says two subintervals. So I smack it in, break it in half. So 1 to 1.2 to 1.4. And then I look at the bottoms there. Okay, so that's the 0.2 and that's the 0.2 for both of them. And then I know that I'm supposed to go in the middle of those two. So the middle of that is 1.1, the middle of that is 1.3. And those are the heights that I'm going to use. That's what tells me I use those two y values in the middle right there. So you'll see all of those scenarios. Again, the good news is we've now seen all of them. You've seen a trapezoidal sum, left, right, and midpoint Riemann sum, and you're going to see all of those again in the future, so you can kind of practice that. But when you integrate between 1 and 1.4 and you do that Riemann sum, notice how I'm getting 4.6, which isn't even close to the 18.2, because that's how far you went in between 1 and 1.4. But you got to take into account, if you're going to start at 1, you got to take into account where you were at 1. Okay, so this is kind of like those initial position problems where you got to take into account the initial position. This is like where we were at after 1 second. And then this tells me where did I go in between 1 and 1.4 seconds there. So that's like your initial thing. And that f of 1 they told us up there, that was equal to 15. So that's where you started. And this just tells you what was your change in between the 1 and the 1.4, and that's the 4.6. So then you add those up, and those numbers are closer to each other right there. Euler's method. I love Euler's method every time I see it on the AP test because it's usually like straight exactly like the BC Extra video lectures that we did, so you can rewatch those if you need to. But the hardest part of these classes is just doing that without the calculator, and this one wasn't bad. So you just make your table. They say Euler's method, x equals 1 is your starting point, 2 equals steps, and you're supposed to end it at 1.4. So that's what tells me that delta x was the 0.2. So I went 1, 1.2, 1.4, and whatever y value I get right here, that's going to be my final answer. So this is your starting point, and they told us that point, just like there, was 15. And then remember, you're supposed to go delta x times dy dx. So you're going to take delta x, which is your 0.2, times your derivative. Now, if they give us a derivative, then you got to take the 1 and the 15 and plug that in place for the x and the y. But here they didn't give us any derivative. They actually made this easier for us. So that just means what's your derivative at x equals 1. And at x equals 1, that derivative is equal to 8. And so I did 0.2 times 8, that was 16. With a decimal over 1, get 1.6. Remember, to get this last number, you add up these two numbers here. So 15 plus the 1.6 is the 16.6. And then that's your new y value. And you do the same thing. So you're going to take delta x, which is 0.2, times it by the dy dx. That's your derivative at 1.2. So at 1.2, our derivative is equal to 12 from the table. And then that would be the 2.4. Add up 16.6 plus 2.4 equals 19. And then that's your final answer right there. Then letter D is our friend, our Taylor polynomial, and I see second degree Taylor polynomial. And so I'm just going to go ahead and use our main definition straight from our videos there. So a second degree, we're going to, and then it says about x equals 1. So our C is equal to 1. So we're going to go f of 1, f prime of 1, x minus 1 to the first over 1 factorial, f double prime of 1, x minus 1 squared over 2 factorial, just straight your main definition of a Taylor polynomial. They tell us f of 1 is 15. They tell us from the chart f prime of 1 is equal to 8. And then they also tell us up here f double prime of 1 is equal to 20. And so then you just go 20 divided by 2, you got your 10. There's your Taylor polynomial. So they wanted us to write that. So that's part of the answer. And then we're supposed to use it to approximate the f of 1.4. So just plug in the 1.4 for the x's. Be careful with your arithmetic. And then that's going to give you your approximated y value. So remember, the Euler's method is also using the derivatives and the tangent line stuff that's close to the actual curve. Remember, the Taylor polynomial is finding a polynomial that's close to your actual curve, and you can actually plug that in. So even though you don't know the equation of that thing to plug in your 1.4, you find a Taylor polynomial that's close to it, and it's giving you that y value approximation. So really good understanding problem. Hopefully that helps us understand, the rest of the Taylor polynomials is just a little bit nicer and stuff there, how all that stuff connects there. Ranch dressing.